Morning everyone. So we're going to continue on with this intro section. Yesterday we started looking at unit conversions. Basically scientific quantities are measured with a bunch of base units called SI units. Depending on the particular order of magnitude, the particular power of 10, we ended up using a prefix, a syllable that came before the word that roughly told me where the decimal would end up. Yesterday we really didn't worry about rounding from the calculator. Today we'll address the notion of why do we need to do rounding, as well as some rules here that pertain to the significant figures that we see. Just for starters here, just for a quick practice question, making sure you are just keeping up with the worksheets. If you have questions, definitely ask so that it doesn't become overwhelming. In an effort to keep these lessons a little bit shorter, I'm not going to do as many warm-up questions, but when I do want to show you something with it, I'll definitely have the question inside. So let's start off with this question here just as a warm-up. Let's imagine the question here is how many decimeters cubed in 4 liters worth of volume? So both of these are actually units of volume. Both of these are units of how much space is being occupied. The reason why this question here is a little bit strange is up to this point, we've been converting same base unit to same base unit. We've been converting things like meters to centimeters or grams to kilograms, things like that. In this case here, you'll notice the base unit has actually changed. This liters here, usually maybe it's a 4-liter milk jug, something like that. Usually we use liquid when we're measuring liquids. It's nice, 4 liters as a jug. But what we're comparing it to is we're actually switching the base unit up to actually a meter cube. So we'll need to look up the sort of relationship between these base units here. It's a little bit strange because we're actually changing base units. This normally doesn't happen. The one conversion I will give you here is to sort of get at doing this conversion. 1 centimeter cube, if I have a box that is 1 centimeter on every side, and I multiply those 3 dimensions, the amount of volume, the amount of space that's taken up by that cube there is equivalent to 1 milliliter. Now the grams may be different because of density. We'll see that later on. But in this case here, at least space-wise, 1 centimeter cube is always equivalent to milliliter. And in that case there, it does the conversion from something with meter cube over to liters. Then I'll need to convert it to deci. I'll need to convert this to liters as well. So let's set up our trusty unit conversion method here. I'm going to start off with a question mark decimeter cube because I know that's my final unit. If you're ever stuck, just start off with the number given. It's nicely for these first sort of conversions, you're only given one number. Sometimes you're given 2. But here we have 4 liters. I know what I really want to do. Don't write this down just yet. What I really want to do is I want to go liters straight to decimeter cube. It's just with that second step here, I may not know that conversion off the top of my head. If the conversion that helps convert base unit actually uses milliliters, instead what I'm going to do, you can write this part down here. Let's go liters just straight to milliliters first. Base unit to one that has a prefix. Then we'll utilize this relationship that was given here. 1 milliliter was equivalent to centimeter cube. You just punch that in there. And that's how we would actually have converted from, we used to be a liter, and now we're over to centimeter cube. And now at this point here, just like yesterday, what we really want to say is we want to go centimeter cube over to decimeter cube. My guess is you don't know that conversion off the top of your head. But whenever we have powers, what we can do is we can do centimeters to decimeters. Just do the 1 decimal place conversion. But do that in this case here 3 times because I have 3 dimensions to cover all 3 sides of the square here. So that's how we're going to set up our work here. Let's go through, stick a 1 beside the unit that's bigger. So in this case here, between liters and milliliters, liters is bigger. 1 liter is actually equivalent to 1,000 milliliters. Perfect. 1 centimeter cube was given to you as 1 milliliter, so that was fine. This one here is actually a prefix to prefix sort of conversion factor here. You could very well have gone centimeters to meters, then meters to decimeters. Because I'm cubing it here, I'm just going to figure out this lockstep here. And in this case here, deci is actually 10 to the negative 1. Centi is 10 to the negative 2. Deci is bigger. So 1 decimeter is actually just 10 centimeters. They're just off by 1 step. 1 step on the metric scale is power of 10. So 1 beside the thing is bigger. I'm going to end up dividing by 10. Now, if you look mathematically, you type this in your calculator, don't bother typing any times 1 or divide ones. What we're ending up doing is we're going 4 times 1,000, so 4,000. We're going to divide 3 orders or 3 tens, and we're going to basically dividing 1,000, and we coincidentally end up getting 4 back. This is not your calculator being broken. This is actually saying after all that work, after all those unit conversions, we actually realized that when we had said earlier 4 liters, we actually also mean 4 decimeter cube. So just like you may have already knew this relationship, 1 centimeter cube is a milliliter, I want you to be able to show me, in this case here I had 4, but I could even say 1 liter is actually equivalent to 1 decimeter cube. The reason why I want you to know this relationship here is IB doesn't like this liter because it's not an SI unit, so not SI. IB would prefer to have the SI unit. If it had a choice, it would actually punch in the SI unit as a straight meter cube, but just for convenience here, we actually just use decimeter cube as well. So IB doesn't use liters. It doesn't mean you can't leave your answers in liters, but when you're reading through questions, it'll prefer to actually use decimeter cube. So for example, later on we'll do a conversion here that's say moles per liter. In that case there, we'll actually be able to shorthand it in regular Chem 11 and Chem 12. We'll shorthand it capital M. IB doesn't like this liters, so what IB is going to do is going to say mole per dm cube. And in this case here, when I have the power in the denominator, I can even write this here, mole per dm to the negative 3. So it would rather write mole per dm cube versus molar, which actually relies on liter. So just like 1 milliliter is 1 centimeter cube, make sure you know 1 liter is equal to 1 decimeter cube. You can verify it for yourself. 1 kiloliter, when we do our gas law section here, that one here actually is our SI unit, 1 meter cube. And they're all off by a factor of 1,000. Yes, I know they're all just one step off from each other, but because there are 3 dimensions to it, I end up tripling that conversion and I end up getting it off by 1,000. So that's all great. It helps you do your unit conversions. You definitely need a lot of practice with that. Chapter 1, a lot of it, sure, we're going to introduce molar mass and molar volume, actually introduce more scientific quantities, but we are going to do that practice. Top unit cancels bottom, top unit cancels bottom. Tack on as many fractions as you want until you get to the final unit. Today I want to address the notion of uncertainties. I want to address the notion of, say a calculator gives you a number. Am I supposed to round that number? When do I? And why do I do it? So in this case here, in chemistry, we're going to do uncertainties. You can just continue on with your notebooks here. You don't necessarily need to start a new page. We're going to start off with a quick thought experiment before we get into these rules here. If you've done significant figure stuff here in physics, it's exactly the same. If you go into physics next semester or next year, it'd also be the same here. We're going to start off with a statement here. Turns out, experimental measurements, when you go in the lab and when you take down a reading, doesn't matter how hard that reading is, the distance, time, whatever it is, experimental measurements can never provide exact or true values. We're sort of limited by the equipment that we're using. If it's not a very good ruler, it's not going to have a lot of decimal places. We're also, so let me just write this down here. The reason why it's not able to give you an exact and true value here, we're actually always limited by the precision. We'll come back to some of these words here in tomorrow's lesson as well. Precision of your, they call it apparatus. Apparatus is just the equipment, the measuring tools that you're using. Apparatus as well as any possible human limitations, human interpretation problems, human interpretation. So let's just do a quick thought experiment just to give us a feel what's happening here. Let's say I just lay down a pen here, and let's say I'm interested in you measuring how long is this pen. So we're going to start off here. The device to measure distance is a ruler. So we're going to line up the ruler on one side here. Little do you know here, when you actually look at that first ruler here, it's maybe those rulers I use in elementary school here. For whatever reason, even though we can line up the pen here, for whatever reason it only has the centimeter tick marks. Right, and onwards in there, we'll imagine it's scaled 2 centimeters. So based on this first ruler, I'm still asking you, I'm just trying to make an experimental measurement. How long is this pen here? In this case here, I'd say, 4.5 maybe? 4.4? Maybe even 4.3, right? So I'm looking at one pen. In terms of this sort of reporting of the measurement, I know I'm confident about this 4. Because provided I line this ruler up properly, I know it's at least past the 4. What I'm not sure about here is actually the next decimal place. The next decimal place here is somewhere in between the 4 and the 5. I don't have those millimeter tick marks to actually figure out what we are. So in that case there, I know this one here, this is called a guess. This is an estimate. I know it could be wrong. So I know I'm looking at the same pen. It's not like suddenly the pen is longer or shorter or whatnot. We're just limited by this ruler here not being a very good tool. would it do me any good if I, using the same ruler, if I said, oh, I know exactly, I just got my eyes checked, 4.362176 centimeter. Would it make any sense to keep a number that's so long? Well, again, let's just analyze it here. Which ones am I certain about? I'm certain about the 4 because it's at least past that 4. We talked about, we were guessing this position, right? I don't have those millimeter tick marks here. I don't know this one. What if this were off? What if this were actually 4.4 or 4.5? Well, that would then say none of these other numbers mean anything anymore. If I was already wrong in this decimal place, there's no reason to keep anything afterwards. Normally how this would happen is your calculator might end up spitting off a long number like that. I would then round it to say, nope, this device only lets me keep it to first decimal place. This number here is said to have 2 significant figures. It has 2 digits of meaning. 2 significant figures, 2 digits of importance. Now, just before we hash out what these significant figures a little more, your friend realizes here you're using a really poor ruler. He gives you a better ruler. What you would imagine here is the ruler at least sure has a 4, has a 5, everything lined up, but should have those little tick marks in between. So let me just line this up for you here, depending on how you end up drawing it. Let's say this is the 4. Okay, so this is just a zoomed in picture, and let's say the pen actually goes up to here. Okay, I can look all your guesses so far, and I can say you're wrong. It wasn't 4.3. It wasn't 4.4. Well, based on the first ruler, that was my limitation. That was my precision because the ruler wasn't all that great. Now that you line it up with a better ruler, now I can say with confidence, oh, I know it's exactly going to be 4 point. Now with the millimeter tick marks, I know it's exactly past the 0.5. So the person who said 4.5 would be right. And now, again, I don't have the tick marks in between the millimeters. I'm having to eyeball one more value. I do keep that value around, even though it might be wrong. Maybe it's 4.54, 4.55. This number here might be wrong, but it does give me a little bit of information. Even though I know it could be an estimate, it could be off, it's giving me information that the next position is probably something less than half. In this case here, better ruler is now giving me more significant figures. So this number here now has 3 significant figures, or you can say 3 significant digits. And what we're going to see here is these significant figures, Sig Figs for short, significant figures or significant digits, they identify for us which digits have meaning. Meaningful digits. Which digits should you keep around? Which digits should you not round off? So in this case here, I had 2 digits of meaning. Just to be case in point here, significant figures contain all your certain ones, all the digits that you're confident about. If you know exactly it's at least 4, well, of course, keep it. There's no point in rounding that one there. But strangely enough here, we're actually going to keep around 1 digit that's a guess. So even though, here's something to wrap your head around here, I could totally be wrong with this guess. That someone could come back and say, no, it's actually 4.56 or 4.57. I wouldn't be surprised. I was estimating this anyways. But I'm still going to keep around 1 guess because it has meaning. It does tell me roughly I look like I'm a little bit less than half in the next position. So while it has meaning, it could be wrong. So in this case here, the 4.54, I'm sure of the 4. This time I'm even sure of the first decimal place, better ruler. But in this case here, this guess, which might be wrong, I still consider it a digit that has meaning because it's telling me it's a little bit less than half in the next spot. There's no point keeping anything any more than 1 guess. So if I had like 4, 2, 3, 7, 1, 9, whatever, in this case here, there's no point in guessing too many. Because the first one could have been wrong anyways, there's no reason in keeping anything afterwards. So that's the notion of Sig Figs. That's how we deal with uncertainties in chemistry. This was a little bit easier because you were the experimenter. I showed you, here's the ruler. When you use a better ruler here, here's what I could get. As you would imagine, the better ruler here, the more significant digits should be a more precise reading. It's not actually the pen itself has gotten longer or shorter. It's just I have a better interpretation and a better feel of what the number is. Now, where does the interpretation aspect come in? In this case here, because I don't have the tick marks in between the millimeters, some people might end up guessing a little bit too high. Some people might guess it too low. It's not that we're reading different rulers or looking at different pens, but based on our judgment, because this guess here is totally an estimate anyways, some of it might ballpark it a little high, a little bit low, and this will be introduced as a random error in tomorrow's lesson. This becomes a little bit harder when we are not the experimenter. When someone just hands you a measurement, I don't know. I didn't watch them actually take the reading. I don't know how significant they're actually keeping the numbers. So first thing I'm going to do here for these significant figures, before we get to the math, is just introduce to you, especially when I am not the experimenter, how do I associate the level of precision based on numbers that they give me. For starters, we're going to begin with the fact a definitions or counting numbers, and what's implied there is a small counting number, an easy counting number. These ones here are exact, or these ones here are going to be true values. They haven't been rounded in the least. An example here, let's say you go to the store and you buy a dozen eggs. So the eggs have already been pre-packed for you. We know a dozen means exactly 12. Does a dozen ever mean 13, 11, 11.6, 11.2? No. A dozen by definition always means 12. Now, as you get to the next two rows here, if you wrote the number 12 like that, that looks like a number with 2 Sig Figs. But in fact here, because this is by definition, I'm actually thinking of this number here as actually 12.00000 to infinity. Because significant digits here only allows for one guess, the guess is always going to be the one that's farthest along the decimal place. That means I'm certain it's at least 10. I'm certain of the 2 in the 1's place, so 12. I'm certain of the 0.0. I'm actually certain of many, many ones. Even if I had a guess, my guess would be over at infinity. So this is why a number that's exact can be referred to as something that has infinite Sig Figs. It has infinite precision, so you don't need to worry about rounding. You don't need to worry about estimating or guessing. In fact, all of the definitions we've seen so far with prefixes, let's say 100 centimeters is a meter, that was by definition. So just like later, when you look at a number like 100, it looks like 1 Sig Fig, but no, this is by definition. Sometimes I use 3 lines for definition. So by definition, I set 100 to be exactly a meter, not 99, not 100.1, but it's always going to be 100 exactly a meter. So that's going to save us a little bit when we get back to our unit conversions. What about the small counting numbers? So small counting numbers can be as simple as, let's say I'm walking to a classroom and I'm interested in counting how many students there are. Now, students are fairly large objects, right? I can identify between one student and another student. Let me do a quick count around the classroom, and maybe I say, oh, currently there are 28 students in the classroom. I'm never going to have 28.5. I hope I never have half a student. But it's a small counting number, and provided you trust my counting, you can say, yeah, 28 is exact. That means, again, 28.000. Now, the trouble is when we start looking at things that are tinier, right? Not a whole student, not a really easy object to count or miscount and double count. But what if I have like particles that are really, really microscopic, really tiny, really hard to identify one particle from the other one there? In that case there, the counting gets to be a little bit harder. So those are the ones that actually don't need significant figures. We don't need to do any rounding. Rule number 2 here. When I'm given a measurement here, anytime in that measurement, if I have numbers 1 through 9, I'm just going to treat them as significant. I'm going to treat them as meaningful. Right? I wasn't the experimenter. I don't know how good their tool was. So let's take a number here. Someone measures the length here of 135.7 centimeters. I have no idea which ruler they were using, the good ruler or the bad ruler, or even a better ruler that I haven't seen. But in this case here, because all of these numbers here are between 1 and 9, I say significant, 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 significant. Right away, I can say 4 Sig Figs. So more Sig Figs here generally means more precise. We'll qualify that statement in a second here. Because significant digits are just the digits with meaning, it means I'm sure of the 1, I'm sure of the 3, I'm sure of the 5, even though I might be wrong. Someone might come back to me and say, no, it's actually 135.6 or 0.5. That's okay. I was allowing me to have one guess. So in this case here, you can make a note to yourself. We actually have 3 certain digits. The guess is always the one that's farthest along, and this time my guess is in the 10th place. It is in the first decimal place there. I might be wrong there, but it still provides me meaning. We mentioned here, well, this is 4 Sig Figs. It should be more precise. Which one of these numbers is more precise? If I have a number like, actually maybe I'll get back to that later on. Let's go to our last rule here. Last rule here is going to be, well, we dealt with digits 1 through 9. What about zeros? Right? Those are the only digits that I haven't talked about yet. The trouble with zeros is sometimes they're important, sometimes they're not. If you did this in physics here, they'd probably get you to memorize a whole list of rules. Okay, I find the easiest way to do this zero is I want you to imagine something called an arrow rule. So it's sort of a rule in a rule here. And basically what this arrow rule decides is it just decides for you when zeros are important, when zeros are not important. For this arrow, you can imagine an arrow. This arrow shoots left for numbers with no decimal. So no decimal points, no decimal places. And the only other difference is it shoots right for numbers with decimals. So if you already know the rule with zeros here, try out this arrow rule, see if it's consistent. Let's take the number like 500. Okay, again, I wasn't the experimenter. I didn't see the person actually take down this reading. But what I want to get a sense of, how many digits of meaning is this number as written? So the 5, I'm sure of, because 1 through 9 are always significant. These zeros here, I'm not sure, because I said sometimes they're important, sometimes they're not. How do I tell? In this case here, 500 here has no decimal place. So I want you to imagine standing over here. We're going to shoot left, shooting a bow and arrow. And what this arrow is going to do is it's going to cut through any number of zeros. When it runs into something that's not a zero, it gets stopped in its tracks. So imagine taking your trusty bow and arrow. You're only allowed to shoot once. I shoot this arrow. Okay, it cuts through those zeros, no problem. When it runs through the 5, it can't cut through the 5 here. What you're going to find is if the arrow has cut through these zeros, it's indicating to you that these zeros here are unimportant. So these ones here are what are referred to as placeholders. These zeros are only important in such a way to put the 5 in the hundreds position. But in terms of meaning, in terms of precision, in terms of detail, those zeros here are insignificant. Placeholder, but they are not significant. So whatever's left over that has been cut through, this 500 as written is a 1 sig fig number. Now I do want you to be careful here. I have not suddenly said, oh, they're unimportant. 500, this one here is 5. Imagine going to the pizza store and ordering 500 pizzas. 500 is very different from ordering 5 pizzas. What I'm saying here is when you write the number 500 like this with no decimal place, where I'm guessing, the one and only number that I have is actually a guess. So you go to the pizza store and you say, oh, give me 500, no 600, no 400, right? The numerical value is still going to be 500 pizzas, but based on writing it this way, I'm unsure at the hundreds position. Now, what if I come back and what if I do the number here 500.0 instead? So same example, go to the pizza store and order 500.0. Again, I was not the experimenter. I don't know how precise this person was counting. But what we're going to do is we're going to apply our rules. So in this case here, because we do have a decimal place, this time I stand on the other side and I shoot the arrow to the right. This time, it gets stopped right away. This time the arrow doesn't cut through any zeros. All the zeros left over are now important. I now have 1, 2, 3, 4 digits of meaning. We now have a 4 sig fig number. All right, 4 digits of precision, don't round any of them off. Because my meaningful digits are going to be all the certain ones and one guess, this time I know exactly the hundreds, exactly the tens, exactly the ones place. Where I'm guessing is this one. So I may be saying, oh, give me 500, no 500.1. I could even go 499.8. That's fine, right? I'm pretty confident about this one being in the ballpark of 500, but where I'm guessing, this time it's in my tens place. This one here is a lot more precise, as indicated by we have more significant figures. Numerically, it's still the same. Numerically, you're still going to end up with 500, but the precision where you're guessing it is actually at the tens place. Now, just for completeness sake here, chemists annoyingly do, what if I had a number like 500 decimal? Normally in math class here, you wouldn't bother with the decimal unless it was point something. But in this case here with that decimal, that says fine, our arrow still shoots to the right, gets stopped right away. This is now the number 500 again, but now I only have 3 significant figures. So that's like going to the pizza store. You're still going to order roughly about 500 pizzas, but this time I'm certain I'm actually guessing at my ones position. This time you go to the store and you go, oh, 501 or 499 kind of pizzas. So you're off by 1 pizza, whereas earlier with the number still 500, I was saying, no, give me 600, give me 400. You notice that precision is a lot lower. So far, the numerical value of all this has been 500, 1 sig fig, 3 sig figs, 4 sig figs. How can I represent this one number with 2 sig figs? How can I represent the number 500 where I want to say my guess is actually in this position? Oh, give me 510 or give me 520 or something like that. In this case here, when I had no decimal, it was 1 sig fig. Even if I had this funny case here, we try to not do this as much, but even if I had this funny case here with the decimal, it was 3 sig figs. That's unsure at the ones place. How can I show you that I'm actually unsure at the tens place? Here's where your scientific notation comes in. In fact, it turns out all base numbers or all base digits in proper scientific notation are significant. So if I try to write this number 500 in scientific notation, 5 times 10 to the 2, with this extra rule, I'm saying everything in the base number is always important. So I'm going to say, let's say 5.2. Let's check numerically. Yep, this means 500. I don't need to do the arrow rule anymore. This one here indicates 2 digits of meaning. This first one here is certain. This next one here is a guess. So this one here would be my case of, oh, I'll go to the store, 510 pizzas, 520 pizzas, 480 pizzas, 490 pizzas. And that's how you represent it with 2 sig figs. So whenever you're having trouble rounding to significant figures, you just basically put it in scientific notation. Last little bit here, we're going to switch over. So that's identifying not just what significant figures are, especially when I'm given measurements, how do we assign significant figures? And now finally what we're going to do is we're going to deal with a calculation. So calculations with significant figures, usually in science we don't just make one measurement, we have to operate on numbers. The calculation rules here for sig figs, they separate between operators here. Let's do a add and subtract operator. In this case here, the rule is going to be, in terms of sig figs, in terms of uncertainty, we're going to round your answer. So round to the least. One way of just reminding yourself is round it to the least decimal places. I'm going to show you an example where that rule actually doesn't work out. I'm going to actually prefer to say round it to the least precise position. We're going to still use decimal places here as a nice memory aid. Oh yeah, this is the decimal place one. I'll show you when it works and when it doesn't work. So let's say, back to my example from earlier, let's say I made 2 measurements. One measurement was with my crappy ruler here, 1.2 centimeters, and then what I'm going to do is I'm going to add a distance with my better ruler here, 3.45 centimeters. The thing I want to introduce to you is calculators doesn't know anything about significant figures. When the calculator thinks 1.2, it thinks exactly 1.2. It thinks with a bunch of zeros afterwards. When you type in the number 3.45, the calculator thinks exactly 3.45, no uncertainty. It didn't know that these ones here were actually measurements. It didn't know that they were significant figures. It didn't know that you were guessing at any given position. That said, we know the guess is always going to be the farthest one along. So if I have 1.2, I know overall it's a 2 sig fig number. That means the tens place is the guess, whereas the 3.45, the better ruler, the guess is actually in the hundreds position. What I'm going to do is, as if we're in elementary school, we're not going to pretend to be a calculator, pretending that these are exact. We're actually going to apply this. Well, I'm actually guessing at that 2 there, guessing at that 5 there. Calculator, in not doing this uncertainty, calculator then spits out here 4.65, no problem. It says exact 1.2, exact 3.45, gives you exact 4.65 here. But now with the lens of sig figs, we're going to say, wait a second. This first one here may have been off. This one could have been 1.3, 1.1. This second one here could have been off as well, 3.46, 3.49. It could be any of that. I want you to decide which of these guesses is worse. Whichever guess is worse, I'm going to round to that position, and there's no reason to keep anything afterwards. In this case here, you should be able to identify here, this first guess position is worse. If this first decimal place is off, that would knock off the tens place, maybe 4.75, 4.55. If this position is off, there really is no reason to keep anything afterwards. And ergo, we have our decimal place rule. This number here has 1 decimal place. This number here has 2 decimal places. The one with least decimal places is the less precise one, so round your answer to also 1 decimal place. While there was a time we used to take an even 5, right? If this is 5 something, you definitely round up. But if this is an even 5, we used to round it to the nearest even. So 4.65, we would have rounded to 4.6. We'll just be normal these days, and we'll just say, even if it's exactly 50%, let's just round it up. Let's just go 4.7 centimeters. And that way we have the precision. We still have preserved our guess. Oh, because the first one was done with our first ruler, not as good ruler, our final answer is only precise to that same position. The reason why they did this rule here, sometimes they call it an even-Steven rule. The reason why they did this is hopefully they were crossing their fingers. Half the time you ran into this 0.5, the exact half case, and you need to round it. Hopefully half the time you would round it tinier. Half the time you round it up to hopefully give you somewhere in between. Like I said, nowadays we're just going to forget that. Nowadays we're just going to say round everything up. All right? So that's perfectly fine. This rule applies for both adding and subtracting. Let's go to a case where this decimal place rule here doesn't work. So let's take the number here. Let's say I have 100 milliliters, and let's pour out 23 milliliters. You'll always have your calculator, so I would say punch it in first. Your calculator spits out here, this is going to be 77 milliliters, right? Calculator thinks exact 100, you pour out exact 23, of course 77. But now let's use the lens of Sig Figs. Let's line it up and let's say, well, I'm going to take 100. Sure, my operator is minus this time, minus 23. I want to get a sense of this sort of 77 millimeters that I have afterwards. If you just purely came along and did the decimal place rule, we'd actually get it wrong. We'd actually say, fine, no decimal place, no decimal place, final answer, no decimal place. What's wrong about that here is, let's take a look at our numbers. 23 is not too bad. 23, the 2 and the 3 are significant. That means I'm guessing at the 3. How about the 100? How many significant figures is that one there? In that case there, you should be able to tell me, well, 100 is like that pizza analogy up above. Those zeros are placeholders. The arrows would have cut through those zeros. The 100, the one and only significant figure that I have, is actually a guess. So where might this happen here? Let's say I had a grad cylinder. Grad cylinders are used to measure volumes, and for whatever reason this one here hasn't been graduated a lot. It doesn't give me the number of tick marks that I would expect to see, but this one here only has one mark and it says 500. I fill it in with water here. It looks like it's gone a fifth of the way up. I said, okay, bottom of the meniscus here, I'm thinking this one here is now 100 milliliters. Could it actually be 200 something? Sure. Could it actually be 0, like 99, 50 something? Sure. Because I only have one marking, this is not super precise. Now, using this notion of Sig Figs here, earlier we said if one of the positions is off, we're going to round our answer back to that position. There's no reason to keep anything afterwards. So this time, unlike the decimal place, these are numbers that are actually larger than 0. So this one here is actually unsure at the hundreds. This is unsure at the ones. Which guess is worse? Hopefully you're able to say to me here, well, the guess that's at the hundreds position is worse. I need to round this back to this position, back to this spot here. The number over here is bigger than 5. I need to round it upwards. I'm going to round 77 back to 100. 100 minus 23 is supposed to be 100. That's exactly what I want you to say. Now, how does this work? Right? Why is this sign so weird? Experimentally here, we took a really bad grad cylinder and we just guessed, oh yeah, I think it's 100. You have definitely dumped out 23. So imagine I have a smaller grad cylinder over here. You pour a little bit of this out here. This line here would have dropped by a little bit. You definitely have enough tick marks on this one, and you can read this to be 23. There's no doubt that you poured out some liquid. But now I ask you the question again. As this water layer has gone down a bit, I'm going to ask you, well, what is the final water inside this grad cylinder? Well, I still don't know. It's still a bad grad cylinder. Maybe I was actually some 200, maybe actually after you poured out the 23, maybe I'm only now closer to that 100 here. So we just need to be careful. Using our Sig Figs rules here, this is what I would refer to as the least precise position. This is the worst guess, so let's round this to the worst guess. So strange as it may be, 100 minus 23 is now going to be 100. That's the rule for adding and subtracting. We can line up the decimal place and make sure we match it up correctly. Multiply and divide turn out to be a little bit easier. So for multiply and divide, because numbers are going to get big fast and numbers are going to get tiny fast, there's no point in lining up the decimal place anymore. What we're going to instead do is, again, we're going to round our final answer, round to the least significant figures. This time here is nothing to do with decimal place anymore. I don't care you have 0.1 or 0.01, things like that. I'm just going to look at the numbers going into the product or the quotient, figure out how significant are the numbers starting off at, and then operating on these two numbers here. So for example, let's take distance here, let's go 5 centimeters, and let's multiply it by 7 centimeters. Okay? Easy. Calculator says 35 centimeters. But these ones here are measurements. So calculator didn't know that these ones here, you weren't really sure of the 5, you weren't really sure of the 7. In fact, both of these numbers here only have one significant figure. You can't end up with something that's more precise than what you put in. So what would this number be if I rounded it to one significant figure? If you're only allowed to keep one digit, we just read left to right here. If we're only allowed to keep the tens position, we now need to round this, again, even 5. Let's round this to 40 centimeters squared. Because this 5 here could have really been a 6 or a 7, 7 times 7 would easily be in the 40s. Because we're so unsure with these starting measurements here, when I round my final answer, it needs to represent that precision as well. Now, what if I did it the opposite way here? What if I did 5.00 centimeters times it by 7.000 centimeters? calculator doesn't care. You don't even need to type in the 0.00. Calculator just treats exact 5, exact 7, gives you 35. But now, based on my rulers, this one here could have been my better ruler. This now has a precision of 3 sig figs. I'm actually guessing that last position here. This next one here has a precision of 4 sig figs. Again, I'm guessing that last position here. I don't need to have a final answer. Calculator thinks exact. So calculator thinks 35.000. That's why it doesn't bother showing you the 0.00. But when I actually show my work, I want to show it to you with the significance of, in this case here, my least precise is having 3 significant figures. What would this number here being rounded to 3 sig figs? So I'm able to keep left to right here, able to keep the 3, able to keep the 5. I'd actually purposely add in the 0.0 myself, so then it represents, well, this measurement here, based on how good the numbers were going into this, that's going to have an impact on my final 35.0. Right? So you see that the rules are a little bit different for add and subtract. That was a decimal place that was lining up the least precise spot, whereas for multiply, as well as we'll see a divide in the next question here, we just simply do the least, round your final answer to represent the same significance as the numbers going into it. There's only one place where you can actually end up with answers that are actually more significant, like more precise than going into it, and that's only more so in the add and subtract case, especially when I add enough numbers. When the particles themselves, let's say I add 1.2, 3.45, I add another 5 centimeters, 7 centimeters, 8 centimeters, or whatever. In total, the sum is going to be actually more than 10, and we're actually going to be gaining significant figures even if I keep the decimal place rule. So that sort of goes along with the lines. If it's a bigger measurement, it should be easier to count. It should be easier to measure. Lastly here, we're going to end off. Let's deal with the mixed calculation. As the name suggests, it's going to have sum plus and minus. It's going to have sum, multiply, divide. Let me give you just a general rule just to keep in mind as we go through this. In general, I want you to keep all digits through your calculation. So don't do any pre-rounding, especially when you're not fully done. Most of your calculators have an answer button. No, it doesn't tell you the answer of every question. It just recalls down the full decimal unrounded from earlier. But we will watch out for sig figs. So I'm not actually going to do the rounding, but I'm just going to watch out. So let's just try out a question here. Let me make up a number. 34.5 divided by 0.095. Let's add that to 1.260 times it by 30. All right, so it could be any math calculation. Again, calculators would just treat these exactly. That's actually where it would start. If you have the calculator, no matter how weird your rounding gets later on, it should still give you the correct numerical value. So what I would start with is just punch the whole thing in. 34.5 divide 0.095. Let's do our bed mass plus bracket 1.26 times 30. Calculator spits out for me here 400.9578, yada yada. Right? So calculator thinks everything is exact, right? That's how math works here. And the numerical value should be 400. No matter how weird my rounding gets, the ballpark should be somewhere close to 400. What we're going to have to do here is we're going to have to do the part separately. So for example, let's do this part. Let's do, what do we get? 1.26 times by 30. Calculator gives me here 37.8. That's an exact number. We've operated through a multiply, so this one here is rounding to the least significant figures. Do your arrow rule, this one has 1 sig fig. This one here should have 4 sig figs. Well, the least precise one should actually be the 1 sig fig. This number should have been rounded to 1 sig fig. If this were the end of the question, I would have rounded this 37.8. I would have rounded it to 40 right away. But because I know this is only part of the question, I don't want to accidentally pre-round this part. Now it's 40, and now end up with an overestimate later on. So I've done both things. I've watched my sig fig rules. This one only has a precision of 1. It behaves like a 1 sig fig number, but I'm still going to carry around the 7.8 just to make sure I don't pre-round. Let's do the same on the other side here. Let's do a 34.5 divided by 0.095. This gives me here 363.15789, yada yada. Again, this is the divide rule. So 3 sig fig number on top, do the arrow rule. This number here would be a 2 sig fig number. You'd still type it in as divide 0.095. Remember, the numerical value is still the same. Where are we precise until? Well, we're precise until this number with 2 sig figs If this were the end of the question, I would have said 360. But again, it's not the end of the question, so I'm just going to circle where I'm guessing. It behaves like a two-significant number, but I want to keep these digits through so it's unrounded. Now, last but not least, I'm going to punch it through an add. So I'm going to combine these two numbers. If I did this correctly here, I should still end up with 400.95. But now that the rule is add, I can then do the plus rule. So if you imagine here, sometimes it helps just by circling where the guess is. I've seen people go like as a tinier number for the ones that are insignificant. Let's add it to 37.8 yada yada. Calculator is still giving you the 400.9578. So far I've said this is sure until the 6, this is sure until the 3. I should round it as sure until that at the tens place here. But you notice I've kept things unrounded. So keep all the digits through your calculation so that I don't accumulate rounding errors. So the number is supposed to be 400, but rounded to that second decimal place, this is exactly like that question we saw earlier. I would need scientific notation. I would need to put 4.0 times 10 to the 2 to get to this answer here. Right? So keep track of your sig figs here. In fact, if this were like a paper 2, like a short answer question here, if they asked you, like, let's say part A, what's the answer? 37.8? I would round that. 37.8, I'd round that to 40. If they say part B, what's this one? I would round it to 360. It's just that when they give you part C and they say what's the total answer, take the unrounded version of both of them if you can to hopefully get an unrounded version of the final answer. So practice through some of the questions on the worksheet there and then just let me know if you have any questions. Thanks guys, take care.